NASA does everything possible to keep our astronauts safe on the station, including keeping them healthy. Even on early space missions, NASA doctors and scientists noticed that astronauts experience bone loss similar to the bone loss experienced by people who have osteoporosis on Earth. One of the very first studies on board the space station characterized bone loss for crews flying long-duration missions. Results from this experiment may help investigators understand bone loss on Earth as well as in space. Lori Meggs with the space station's Payload Operations Integration Center at Marshall Space Flight Center in Huntsville, Alabama, caught up with Tom Lang, the lead scientist on SubRegional Bone Investigation. He discussed his findings and what we're doing to counteract the effects of microgravity on bone tissue.
This study took place on the first 8 expeditions of the ISS, and it was justified by the results of a very important previous study on Mir, which showed that Mir cosmonauts, when you measured them with bone densitometry before and after their mission, lost in a month of spaceflight the equivalent of the bone density lost by an average postmenopausal woman every year. So 1 month of bone loss in microgravity equaled about a year's worth of bone loss, in this sort of clinical population on Earth. We had the privilege of working with, this brand new ISS, and we started when the Expedition 2 docked with the ISS. And what was interesting about our study is that we had 3 time points. We had pre-flight, post-flight, and 1 year after flight to look at recovery of bone. And in addition to that, we used an imaging modality called quantitative computed tomography. It uses the same CT scanners that one uses in a hospital, but there are special calibration techniques and special image processing techniques that allow us not only to look at bone mass, but really to almost dissect the bone. In this case, we were looking at the vertebrae and the hips, looking at bone dimensions, bone structure, subregional bone density, as well as being able to quantify bone strength.
So it's been 8 years since you wrapped up your investigation. What did you learn, and how are we using that information today?
So I thought we had some very important findings. So we can look in 2 ways. One of them, what happens in this group of astronauts who flew on these first increments of the space station. What happens between launch and landing? And there, what we found was that just looking at bone density alone by standard techniques really concealed interesting things that were happening in different small subregions of the bone. And what we saw was that with spaceflight, the cortical bone changed at roughly the same rate as the change in overall bone density, which was very much the same as what we saw in Mir. So we saw the same sort of bone density changes on the ISS as we saw in Mir. But when we looked in more detail, what we saw is that the trabecular bone was being lost at 50% higher rate than the cortical bone or the overall rate of bone density. We found that the loss of bone strength outstripped the loss of bone density by standard bone densitometry techniques by 50 to 70%. And that's a very important finding because really bone density is not a very meaningful concept biologically or in terms of fracture risk. A fracture is the failure of a bone essentially as an engineering structure. The structure of the bone cannot hold up to the forces in a fall, for example. And so what we need is a direct estimate of bone strength. And so we found that that was changing very rapidly. And then we were able to look at the recovery data. And what we saw was that if we just looked at bone mass alone or the volume of cortical bone, essentially the losses were recovered. So effectively, a year after their mission, the astronauts, in terms of their bone mass or their standard clinical bone densitometry, were about where they were when they launched. But what happened was with the CT, we could measure what's called the volumetric bone density. And that is a bone density which is independent of size. That really did not recover. But what happened was the mass of the bone was recovering because it was growing bigger. So to accommodate these renewed stresses upon landing, bone adapted by increasing its size. And that is something that we see in aging. So if we look at the hips of the hip of a very, a young, healthy person, and we compare these to people of the same race and gender who are 5 decades older, what we see is tremendous age-related bone loss in these older people. But these older people, even when you correct for differences in body size, have larger bone dimensions. Their bones are growing bigger to deal with the loss of aging. But we were able to see in a year what it takes decades to see in Earth studies. And the biology of what we were able to see with our NASA studies really sheds light on this very important aspect of the biology of aging. In space, one is under microgravity, one is close to weightless, and the load on bone is removed and bone is lost. And so the philosophy of exercise is you counteract this by restoring those loads on bone, making people lift weights, etc. But the weight machine in these early missions was a very limited functionality. You couldn't lift very much, you couldn't do very much with it. And in 2008, they lofted a monster of a machine called the Advanced Resistance Exercise Device, or ARED. And this thing allowed for 600-pound loads, tremendous flexibility. It was a more reliable system. And so they undertook a study of, if you do this very high intensity resistance exercise, would it have benefits for bone if it were combined with very good nutrition? Because one of the things that was found in the early astronauts was that they just did not get enough of their daily energy or protein requirements, that this was important for bone loss. A study was done on 5 astronauts who exercised on this ARED device and had carefully monitored nutritional status where they got everything they needed in terms of energy, protein, other nutrients. And it was found that their bone density loss appeared to be less than the previous crews of the space station, as well as the Mir crews, and that, in fact, this could potentially be successful as a countermeasure. I mean, those were only 5 data points, but it was very encouraging. It fills in the overall clinical picture and gives an important data point, because really to develop medicines to treat osteoporosis and to understand which of these medicines to use, and to understand, for example, this is a question of physical activity. Bone changes when the load on bone is increased. So for example, when our astronauts returned having lost a lot of bone and then they recovered and their bone size increased, it tells us a lot about how bone responds to mechanical loading. It gives us information about how bone might respond to exercise, about what might happen to individuals who have been for a long period of time in bed rest or who have been otherwise sedentary but who become mobilized again. And so it's information that can be used to develop a better picture in clinical research and in understanding how people with different conditions recover from those conditions. NASA has been working very hard on developing countermeasures to bone loss. So I think the main importance of our results for NASA were to really illustrate that, okay, folks could come back and they could recover their bone mass, but their bone structure was irretrievably changed to look like something of the structure associated with increased age, so that in fact, with these changes, people might have the skeletons of an older person, and decades down the line might have, poor skeletal health as a result. So this highlights the importance of preventing this from happening.